So the next thing that I want to discuss is vacuum energy. So vacuum energy plays a very important role in quantum field theory and also in cosmology and many other branches of theoretical physics. So it won't be possible for us to go in great detail about this subject, but I will give you some interesting tidbits about it. So in the complex scalar field, as in the real one, we subtracted an infinite quantity from the Hamiltonian to deal with the infinite vacuum energy. So this was basically the vacuum energy that was associated with the zero mode of the harmonic oscillator. Because we can think of the free quantum field as a collection of an infinite number of simple harmonic oscillator in momentum space, we expect the vacuum energy to be infinite. So instead of doing the subtraction, we could have done it by much more efficiently by introducing what is called normal ordering. So we could have done normal ordering of operators. So what does normal ordering mean? It means that suppose you have a collection of operators, say A dagger, B, B dagger, etc. And now if you have a product of these operators, say the product is A dagger, say A1 dagger, B2, B2 dagger, A1, A3, then the normal ordered product is denoted by these colon signs around the product. And what normal ordering means is to reorder this bunch of operators such that all the annihilation operators are pushed to the right and all the creation operators are pushed to the left. So this normal ordered product would be A1 dagger, B2 dagger, and then B2, A1, A3. So let's take a minute. So what would happen if you didn't have normal ordering? Suppose we just had this, product of operators, and we wanted to, express them in a way such that the ordering was something like this. Then what we would have to do is that we would have to use their commutation relationship. And so what we would get on the right-hand side is this term, but in addition to this term, we would get a lot of other term, which results from the commutation relationships between these operators. Whereas when we are doing normal ordering, when we find that the normal ordering prescription means that inside the normal ordering, we can move the operators around, and then when we remove the normal ordering, they have to be ordered in such a way that all the annihilation operators are on the right and all the creation operators are on the left. So if we were to write the Hamiltonian as a normal ordered operator, then inside the Hamiltonian, we have the usual quantities which are not operators, and then we would have the normal ordering of, say, A dagger A plus A dagger. So this is the case of the real scalar field. And remember that when we wrote this term in this way, that's when we got the infinity. That's where we get the 0-point energy. Oh, there was also a factor of half. So when we get rid of the normal order, what we get is, so there's a factor of half. The first term is already normal ordered, and the second term has to be written like this. And therefore, we would get A dagger A without the infinite term that we would then have to subtract. So when we discussed the simple harmonic oscillator and we wrote down its Hamiltonian, we had the A dagger A term, the number operator term, and then plus half. And then this was multiplied by h bar omega. Now we said that this is the vacuum energy. So the vacuum energy, the lowest energy of the harmonic oscillator was half times h per omega. And this had a physical interpretation. Although we could not, use this energy in any way, it had a physical interpretation because without this vacuum energy, the Heisenberg uncertainty principle would not be valid for the ground state. And we know that for the ground state, the Heisenberg uncertainty principle satisfies this equation. So the vacuum energy has physical presence. And that can be seen in a very nice experiment that's called the Casimir effect. And the Casimir effect has been experimentally verified. So let me describe the Casimir effect. So suppose that you have, we can think of the quantum field as an infinite number of oscillators. That is, something that has all the frequency in Fourier space. Now, if I take the Fourier transform of this, what does it mean for fluctuations in physical space? In physical space, it means that there will be oscillations of all wavelengths. Now, Casimir's brilliant idea was to test this. And his idea was to basically put two uncharged parallel metal plates very close to each other. And he surmised that, okay, if the vacuum just consists of, quantum field fluctuations of all sizes. So what Casimir did is that by putting this, parallel plates, he is essentially forcing any wavelength that is greater than, the separation between these two plates. They cannot exist between these two plates. So although, any smaller wavelength can exist, there is an upper cutoff to the wavelength. And Casimir, what he asked is that, he asked whether, the fact that, there is an upper limit to the wavelength in between the two parallel plates, whether or not that has a physically measurable effect. And he found that yes, it does, and that there would be a force between the plates, although the plates are completely uncharged. Casimir did this, proposed this experiment in the context of the electromagnetic field because he thought of the vacuum. He was thinking of the electromagnetic vacuum, and we can do the analysis for a scalar field, and the results are quite analogous. And of course, Casimir was doing his analysis in 3+1 dimensions, but for simplicity, we will do it in a 1+1 dimensional quantum field theory. So in our case, the plates are going to be just like dots because, so this is our one-dimensional space, and the plates will be, something like dots. But, essentially what we're doing is that we are imposing the boundary condition that in between the plates, the longest half wavelength can be of the size A. To count the number of modes, what we're going to do is that we're also going to take initially the length of our world to have length L. So this is, at the end of the exercise, we're going to take L go to infinity, but this is just for convenience. So the question we're going to ask is that what is the energy that's going to contain in an interval D where, at the end of this interval, we're imposing the boundary condition that the waves have nodes. So in that interval, the frequency of the oscillators would be given by omega n, and that's going to be n times pi divided by t. So this is the angular frequency, of course. and this is going to be the n is the frequency. So the energy associated, with all these frequencies, the total energy would be the vacuum energy. We can write that as a function of d. And each mode is going to have energy half times omega n. And we're going to add n from 1 to infinity. So the total energy in our world, 1 plus 1 dimensional world, will be the energy between, say, this interval, and we can just make this to be a periodic boundary condition. So we can just identify this point with this point, and then the energy for the rest of the universe will be E, which is a function of L minus A. So from this relationship where we have n goes from 1 to infinity, and then we have half times n of pi over d, we can write E of A to be, say, 1 over A, and then this guy is going to contribute 1 over L minus A. And from each of these, I'm going to get pi over 2, and then I'm going to get a sum over n from 1 to infinity of n. So if you look at this, let's just look at this part. What is the result of this sum? Well, formally, it is divergent because this sum is nothing but 1 plus 2 plus 3 plus 4 plus 5 dot 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 until it goes on forever. So does this make sense? Well, this is where regularization schemes come in. And there are many ways of regularizing this result. And I'm just going to mention two. The first one will be kind of a mysterious one, which actually has very deep mathematical rationalization. And the second one will be more physical. So the first one is that we can use what is known as the zeta function regularization. And zeta function regularization tells us that if we have a divergent series of this form, not only do they add up to something finite, they add up to a negative number, minus 1 over 12. So if I use this, then the total energy is going to be given by 1 over A plus 1 over L minus A times pi by 24. And therefore, we can work out what the force is between the two parallel plates, and that'll be given by del E by del A. And if we do this calculation, in the limit where L goes to infinity, which is the limit we are looking at, so in the limit where L goes to infinity, we get the force to be minus pi by 24a squared. So this is the force between the plates, minus pi by 24a squared. A very nice and finite result. So even though the energy is formally infinite, it gives a finite result. Anyway, but we use this kind of magic formula here without explaining it. So let's do a more physical, let's derive the result in a more physical way. And the physical thing to do is to say that, well, the high frequency or the short wavelengths don't really interact with the plates because the plate is made out of molecules and atoms, and there are intermolecular, distances and atomic distances, and any wavelength that is smaller than those distances is just, they're just going to seep out. They're not going to be contributing to the vacuum. They're not going to be interacting with the plate, and therefore, if you're calculating, the energy of an interval E of A, what we should do is that we should just like introduce a cutoff delta, a very small cutoff, such that any wavelength or half wavelength shorter than delta should not contribute to the energy. So we can do this if we just write the energy as, say, 1 over A, and then we have the pi by 2, and then the sum, which goes from 1 to infinity, times n, but now we introduce a cutoff factor. So e to the power minus delta n of pi of a. So that, when this thing is of the order of a, this just, it becomes significant. And then for n greater than that, this uh, just goes to zero very rapidly, suppressing the sum at the higher values of n. So this is a physical way of introducing a cutoff. So we can now, compute this sum. So let's just compute n equals n going from 1 to infinity of n e to the power minus delta n pi over a. And this we can write this as, the derivative with respect to delta, and acting on, say, e to the power minus delta n pi over a. So this derivative just brings out a factor of n pi a. So we have to multiply it by a by pi, minus a by pi. All right. So now let's look at this sum. This is nothing but n goes from 1 to infinity, e to the power minus n of x, and this sum is a very nice sum to do. It's just 1 over 1 minus e to the power minus x. And so the sum where n goes from 1 to infinity times n times e to the power minus n of x, this just becomes minus a by pi, and then what we do is that we apply the derivative operator onto this guy, and what we get is we just get e to the power x, after a little bit of algebra, e to the x minus 1 whole squared, where of course we're taking x to be delta pi over a. Now, what you can do is that you can expand e to the power x divided by e x minus 1 squared, and we want to calculate it to order of up to order delta squared. And if you do this carefully, and there's quite a few terms, and it'll be done in the appendix, you find 1 over x squared minus 1 over 12 plus order of x squared term. So using this, what we find is that the total energy, E total, is given by a term that is independent of any of the distance, of the small distance a. So we get 2 pi del squared, and then we get minus pi by 24 times 1 over a minus 1 over L minus a plus order of del squared terms. So we can now, work out what the force is. The force will be minus e by minus a, and we can take the limit where L goes to infinity. Anyway, the first term goes to 0, and then The other term just gives me minus pi by 24a squared, which is exactly the result that we got in our other way of computing the force between the two plates. So this is a very important result. And Casimir was able to show that, you know, the result is independent of the regulator that is used to regulate that infinite sum. So this is a very robust result, and it's a very physical result.